So I'm going to talk about research and clinical trials. And after I'm finished speaking, Anton will answer all your questions on adaptive technology. He's not going to do a presentation, but whatever you want to know, he will be able to answer you. So can we start, Corinne? You can introduce me if you like.
Claudette, you certainly don't need introduction. Claudette has been involved with Retina South Africa for 40 plus years and also with Retina International, where she's extremely highly regarded, not only for her knowledge, but her competence and her ability to organize and to share concepts. And from a personal point of view, I will just say it has been an honor for me all along to work with Claudette. She's amazing at sharing knowledge. Her willingness to help support and be with the team is a masterclass in how to be in that role. Claudette, over to you. I think everybody knows you.
Thank you very much, Corinne. And I must tell you, Corinne hasn't been with us that long, but she has fitted so seamlessly into the team, and her skills are fantastic, and she's brought all her expertise to help us at Retina South Africa. So today I'm going to talk to you about Stargardt disease. We will have other seminars like this, very specialized, and Corinne will certainly, I know, be doing a seminar for us on diabetes and diabetic retinopathy one of these days. So I'm head of science, and for those of you who've seen this slide for the last 20 years, I do apologize. But there are some new names that I don't recognize, and I just want to explain to you how the eye works if you don't know. If you don't understand how the eye works, you won't understand when we get to the complex issues of research. So let's track the light as it comes into the eye through the front coating of the eye, the protective coating called the cornea, which starts to focus the light through the hole in the middle of the eye, which you call the pupil, and then it goes through the lens, which is nature's spectacles, and further focuses the light. So as the light travels through the center of the eye, called the vitreous, it then comes into contact with the retina. And it has to be focused, otherwise you get distorted vision. And for those of you who don't understand a retina, I'm sure you've all got smartphones, and you know that when you take a picture with your smartphone, inside the smartphone you've got microprocessors that take that light coming in and process it and send it to your photo file where you see it as a picture. It works in a very similar way to the retina, which lines the back of the eye. This is a very good picture of what a retina would look like if you could make it as large as this. The back of the eye is that thick coating that you see around the eye, the sclera. Then you get the blood vessel supply, and then we get Bruch's membrane, which we're not going to worry about. Something we need to know a lot about, especially for Stargardts, is this, the pigmented epithelium, which we talk about the RPE. So when I speak about the RPE, I'm talking about that layer. Then you get the photoreceptors, and then this very important neural layer. Let's go and see what that looks like. Here we said we got the light coming in, and it goes through the optic nerve, it goes through the neural layer, and then it comes into contact with the photoreceptors. You see some of them if you can see the slides. If you can't, don't worry, I will be talking to every slide. So some of the photoreceptors are cones, which are more concentrated in the center of the retina, which is called the macula. And although they're colored here, red, green, and blue, of course they're not colored that color. They actually react to light in those colors. There are three, you see red, green, and blue, and now they've just discovered there's a fourth type of cone, which is a yellow, it reacts to yellow light, and these people see the most amazing colors that we don't see. The light then reacts with the photoreceptors, and then this amazing journey of phototransduction occurs. So the light, once it's reacted with either the cones or the rods, is converted from a light to a neural impulse. It then goes from the photoreceptors to the horizontal cells, where very complex biochemical reactions start to happen. It then goes to the bipolar cells, more reactions, more changes in the light, then to the amacrine cells, and then to the ganglion cells. Now, for those who can see, you'll see that the ganglion cells have got little tails or axons, which are long neural fibers, and they group together to form the optic nerve and take this completely changed and coded message along the optic nerve to the brain, which is where you see. I have put some stars there to remind me to tell you some very important things. This layer of cells, remember I said it's important for Stargardts, called the RPE, the pigment epithelium, is the nurse layer of cells and also gets rid of the waste products. And in Stargardts, the initial problem is here in the pigment epithelium with a build-up of waste product. And cone inactivity first and then death later is a secondary process. There's also a red star to remind me to tell you here that even when your photoreceptors are not working, this neural layer of cells is still pretty intact, and that's very important for the researchers, and we'll get to that later. So what causes retinal disorders? Genetic mutations or mistakes that produce toxic or missing proteins in the retina. And these cause the death of photoreceptor cells and progressive loss of vision. In Stargardt disease, the gene mutation interferes in the vitamin A cycle. This is not pure vitamin A, it's a vitamin A retinoid, and it's a very complex cycle. I'll explain it to you later. And because that cycle is interrupted, you get a build-up of a toxic form of vitamin A called vitamin A2E, which is the main component of the waste in the RPE, and we call that lipofuscin. And then, as I said, the cone death is secondary. So let's track the light. So you've got here, if you can see, on the left-hand side of the screen, you've got the capillary, which is the blood vessel, which is bringing the nutrients to here. This is the retinal pigment epithelium. Remember, we said that's the factory part of the cell. And then there's a matrix between that and the photoreceptors. This is designed for a rod because it's rhodopsin, but it's the same for a cone, which is conopsin. So the light is now entering the eye, and it is reacting with the opsin, either the rhodopsin or the conopsin, and then something magical starts to happen. There is a reaction, and the rhodopsin or the conopsin is changed. A neural signal is released, which goes along those neural cells, and the opsin, the rhodopsin or the conopsin, is reduced to opsin and releases all transretinal. You don't have to worry about the names. That changes to all transretinal, which is available to go back through this matrix to the pigment epithelium. And then these various steps of conversion of the vitamin A retinoids happens until it reaches a form of 11-cis that's available to go back over the matrix, react with the opsin, and to form again the rhodopsin or the conopsin, and then is available again in the tiniest fraction of a second to start this whole reaction again. Now, in ABCA4, in Stargardt's disease, the gene mutation stops this ladder of conversion from the all trans to the 11-cis retinal, and this vitamin 2A builds up in the pigment epithelium, clogs up the system, and then the vision starts to be compromised. So you don't have to, it's just to explain to you that to know, you don't have to memorize it, I promise you. So when is Stargardts not Stargardts? Well, you know, in the early stages, it's very difficult for anybody to tell, even an ophthalmologist. And I'm sure some of you got very frustrated early on in your journey when you were first probably told that you had a macular dystrophy. And then somebody along the line said, actually what you've got is cone dystrophy. And then maybe somebody said, actually you've got Stargardt's disease. Or they might have said, you've got cone disease or cone rod disease or fundus flavimoculatus. All of these can be caused by mutations in the same gene, that is the main focus of our talk tonight, which is the ABCA4 gene. But there are other genes that can also cause them. The age of onset is important because that can help people decide what you've got and the kind of mutation you've got, because that's a very big gene. And it's probably not Stargardt's when it's dominantly inherited, but there again, that's a bit of a gray area. or when there's an early loss of night vision, it's probably cone rod dystrophy. So if you've been given one or all of these conditions by an ophthalmologist, one of those diagnoses, they're not wrong. They're all probably correct, but not specific enough for what we need. So how do they know what you've got? Well, they've probably given you some diagnostic tests. The first test, of course, is for your visual acuity. That's when you sit in front of an eye chart and you see those letters, and the optometrist says, read the first line, read the second line, read the third line, and the letters, as you go down the chart, get progressively smaller. You will also have probably a fluorescein angiograph, which was where they inject a dye into your arm, and they actually track that through the retina, and it gives you a dark choroid. So that build up shows won't let the light through to the back of the eye. They will also probably give you a fundus autofluorescence, which is a FAF, which shows up atrophic spots in the pigment epithelium. You might also be given a OCT, which is like a scan of the eye, and it looks like a green sandwich. If you've seen that picture, that's what it is, and it can actually show very specifically and down to a very high level of magnification the photoreceptor damage, and also the death of the outer retina, the pigment epithelium, and the choroid. And of course, the most important diagnostic test after you've had all of those is a genetic diagnosis. So let's look at the genetics of Stargardt disease. Well, first of all, it's recessively inherited. We'll come back to that. So it means if you have Stargardts, your offspring are obligatory carriers of a single copy of a gene with a mistake. The ABCA4 gene, which is the most common gene associated with Stargardts, is on chromosome 1. There are over 600 mutations already identified within that gene, so it's a very large gene. And the latest collaborative research has found unique mutations in deep intonic part of the genes. So some of you might have had a genetic test and they've said, we've only found one mutation and we can't find the other. And that might be because these different parts of the gene, the part of the DNA where you expect to find the genes that are actually the recipes for the proteins, is called the exome. There are between the exomes parts of the gene that they call introns, which they always, believe it or not, 10 years ago they called junk DNA because they actually didn't know what it did. But now we know it's responsible for the epigenomes, and we're now also finding mutations in the ABCA4 in the introns, which is not where we expect to find them or where they should be. It's like if you went into your kitchen and you go into your cutlery drawer and you go to the knife drawer. That's where the knives are. You don't look anywhere else. You found a spoon there, you think, who put this spoon there? So it's like that the coding gene, part of the gene, is being found in the wrong place, but they are finding them, which is good news. So it means we are starting to find all these missing mutations. So let's look at recessive inheritance. In recessive inheritance, you have a mother and a father who each have a single copy of the gene. So everybody's got a double copy of a gene. So this mother has got a copy of chromosome 1 with a good copy of the gene, and she's also got a copy of chromosome 1 with a recessive part of a copy of the gene, the small a, and likewise for the father. So at conception, and remember this can happen every time there is conception, the child may inherit a good copy of the gene from both parents, double capital A. That child will not be affected and not be a carrier. But these two children have a chance of inheriting a copy of the mutated gene from the mother and a good copy of the gene from the mother, or vice versa. So there's a 2 out of 4 chance that the child will be a carrier. A 1 out of 4 chance that the child will inherit a mutated copy of the gene from both parents. And I know these pictures of boys and girls, but remember, it's not gender-based. It can be boys or girls. So the chances then of having a carrier status in the family is the highest risk. 2 out of 4, 50% chance 25% chance that the child will not have any mutation, and a 25% or 1 in 4 chance that the child will inherit a gene mutation from both parents. So let's look what that means. So you're here, you've got 2 normal copies of the genes, copy 1 and copy 2. Remember, you inherit 1 copy from your mom and 1 copy from your dad. Both copies have got a normal ABCA4 gene, and the gene product is produced. There's no problem. Here we have carrier status, where 1 copy of the gene is normal and 1 copy of the gene is not. It's mutated, or it's got a mistake. So the one with the normal one is producing the gene product, and here the one with the mistake is not producing the gene product. But you've got the gene product, so you will not experience or exhibit or express the eye disease. But here, this child has inherited a copy of the gene with a mistake in both copies of the ABCA4 gene, and no gene product is being produced. And that is why the child expresses the condition. So for the Stargardts people themselves, I don't need to show you this picture. You know very well. You have poor visual acuity. It's very difficult to read, to write, to recognize faces. Your color vision may be slightly affected or not even, sometimes completely normal and sometimes quite bad. It's juvenile onset usually, but it's very variable. And remember, fundus flavimoculatus that the doctors still like to use is probably late onset of the same condition. So what are clinical trials? You need to understand clinical trials, because then you'll understand why it's taking so long to find therapies. Well, clinical trials are voluntary human studies designed to answer specific questions about safety and effectiveness of drugs or other interventions. They're registered and controlled and are usually in 3 phases. If you're a researcher working in a laboratory and you have a wonderful idea, or you find a new gene and you think, wow, this is going to cure Stargardts, what do? Well, first of all, you have to investigate it. You have to go into the laboratory and look at what's happening on a biochemical level or at a genetic level until you understand exactly what's happening with that gene or that intervention. And then you have to go to what we call cell trials. You go and look at the identical, what's happening in the gene product, in the protein. Luckily with stem cells, we are now able to grow disease in a dish. So you can actually grow the specific disease, and then you can go and have a look at what's happening in the dish. If you're finding your way and you're finding answers, you can then go on to what we call animal models, usually mouse models, and you can test your theory or your hypothesis to see if it's working. Am I on the right track? And those we call preclinical studies. Now, that might take a few years, and if you're lucky enough to find a sponsor and who believes in you and you can prove that it works, you can then register for a clinical trial. You have to go to a registering authority and show them your data, and they will agree for you to do a very small controlled trial with just a few people, and usually phase 1 clinical trials are only for safety. If after 2 years or whatever the time lapse may be, and you have got good results, you go back to the registering authority, you show them your results, that it's safe, and then they will say, okay, now you can go to slightly more people, and that's what we call a phase 2 clinical trial, and that might also take 2 years. Then, after 2 years, you've now looked at the dosage, you've looked at safety, and you think, gee, this really works. So you can go to the authorities again, show them your data, show them your outcomes, which have to have been decided right up front. How are you going to judge if this is working or not? And all things being equal, they will give you approval for a phase 3 clinical trial, which is far more people and is usually a multi-center trial. Then after your 2 years or so, you can then take your good results back to the registering authorities, and they will register your drug, and you can go out and cure thousands of people and make a lot of money. So that is how clinical trials work. What promising treatments are we looking at then in clinical trials? Gene therapy, stem cells to grow new retinal pigment epithelium, because remember we said the RPE, the nurse layer, is involved in the continual renewal of the visual pigments and the photoreceptor outer segments. Cone cells might be inactive, but they are often still viable. They're not dead. We used to think they were, but now we know they might just be inactive. But the neural cell layer may be still intact. And because it's a similar disease pathway to age-related macular degeneration, that's good news for Stargardt's people. Age-related macular degeneration follows a similar disease pathway for a very different reason. The patients with AMD also get built up in the RPE. It's built up for a different reason, and it's a different kind of a build up. But if they can look at renewing that RPE, it's going to benefit Stargardt's patients. For every one Stargardt patient, there's 100 AMD patients, so it's going to be more viable for drug companies to put money into those kind of treatments. And we've also got drugs that may slow down the build-up of the lipofuscin in the pigment epithelium. So let's look at gene therapy. What is gene therapy? We said in recessive inheritance, you've got 2 copies of a faulty gene, and why don't we just replace one of them with a working copy? And it can be delivered by a viral vector, either an adeno-associated virus or a lentivirus. Or we might use a viral vector to deliver a gene into the retina that we want to produce a therapeutic substance. And we'll talk about that when we talk about photoswitches. And this is how we do it. Every living organism has DNA. So we'll take a virus. The AAV virus is the safest virus to use. And they take out the DNA of the virus, and into that they insert a copy of the gene, the DNA, the good copy. They then replicate it, because viruses replicate easily, make thousands of copies, and with a hypodermic syringe, they will actually introduce it into the pigment epithelium. And I think it's miraculous that the pigment epithelium gets this new, completely new code that they've never seen before. And they say, hey guys, look, we've got a new code, let's try it. And they do, and it works. So gene therapy, I think, is completely miraculous. So let's look at gene therapy for Stargardt disease. Well, I'm sure a lot of you have heard about the Stargen trial for years and years and years and years. And the trial has been halted for various reasons. Because the ABCA4 gene, as we said, is a very, very big gene. And it didn't fit into the working horse of gene therapy, which is the adeno-associated virus. Very safe, very good virus. They know it very well, it works very well. So they did try to put it into a lentivirus, which is a bigger virus, but they did have problems. But the good news is that AGTC has a new approach. It's a dual vector. So what they're doing is they're splitting the gene into 2 sections, and they're putting them into 2 different copies of the AAV virus. And luckily, it seems to be combining in the retina to form the full gene. And they're having success in animal models. And all of this was being developed by Professor Bill Houseworth. Some of you will remember he was the researcher who made all that wonderful progress in the dog models for the LCA gene therapy, which is now gone commercial. And he actually visited South Africa. I don't know if you can remember, a couple of years ago. But the good news is that because it's going to be applicable to other large genes, that funders like the American Foundation Fighting Blindness are putting a lot of money into this dual vector approach, and it's good news for Stargardts. So let's look at the clinical trials. As we said, the Stargen trial has been suspended, and one of the problems was with the lentivirus, and also Sanofi, who was funding a lot of it, decided to move their focus to vaccines. And this was pre-COVID, let me tell you. So you can't blame them. And of course, they're now at the forefront of developing a vaccine for COVID-19. There are visual cycle drugs to disrupt the visual cycle, to reduce the lipofuscin build-up. And the Emixustat is one, it's in phase 2, in fact, 2/3 clinical trial. And there's also soroprazan, which is in phase 1. There's also a very interesting trial called Zimura, where they're looking at the complement C5 system. and it's an intravitreal injection, and it's in phase 2B, and it's looking very good. There's also TEAS, which is a phase 2 to replace the toxic vitamin A2 or vitamin A dimers in the pigment epithelium, and those results were expected in March 2020 but have not yet come out. There's also an omega-3 study on dry AMD and Stargardt. Remember I said for every trial that they're piggybacking Stargardts onto AMD trials, it's good news because of numbers. Then they're also looking at things like saffron and omega-3 and microcurrent and acupuncture stimulation, and we can talk about those later. Stem cells. Well, stem cells are pluripotent cells. They occur in the very early development of the embryo. They're supercells. They can become and do become every cell in the body, but you can also get induced pluripotent stem cells that can be grown from other body tissue like blood or skin or bone marrow. And researchers are growing both photoreceptor cells and retinal pigment epithelium cells from both of these, from the embryonic stem cells and also the induced pluripotent stem cells. And the AGC clinical trial to grow new RPE cells in AMD and Stargardt disease is ongoing. And the Estella trial has actually stopped treating people, but they're doing a long-term follow-up. There are other therapy pathways that are interesting, like pharmaceuticals, optogenetics, and gene editing. So let's look at photo switches or optobionics. Remember we said that even when the cone cells are inactive or degenerated, the neural cell layer remains intact. And the researchers said, well, why don't we just take that layer of cells, it's working, and just make them light sensitive? And that's what they've done. They're genetically delivering a naturally occurring photosensitive molecule called channel rhodopsin, and they're delivering it to the ganglion cells, and there is a patient trial underway. But a very interesting lady called Professor Sheila Nirenberg, about 5 years ago, said, hang on a sec, we can't just take light and deliver it to the ganglion cells. That's not how the message reaches the ganglion cells. It's got all these layers of neural cells that it goes through. So by the time it reaches the ganglion cells, it's a completely different language. And she spent the last 5 years trying to find out how that impulse is coded so that when it gets to the ganglion cells, it's in a language that the ganglion cell understands. So she has now got bionic sight, and they've just tried their first patient out of 20. So what they do is they treat the patient with a gene therapy to deliver a molecule to the ganglion cells. And then there's a device that generates and delivers the same pattern of electrical impulses that the cell understands, so that when it moves the message along the optic nerve to the brain, it's in French and not in English, or English not in French. So she has treated the first patient, and I'm putting my name down. I think it's very exciting. Let's look at gene editing. We said that the code, the DNA that is delivered to the cell has got a mistake. So some people are saying, well, why don't we fix the mistake? Let's edit it out. And this is like if you've got a computer and you use cut and paste, you're doing the same thing, you're editing. And this is what they're trying to do in genes. And Harvard says they can even edit now a single letter in the DNA chain, which is very exciting. Then you also get messenger RNA editing, and it's an antisense nucleotide, which is interfering, instead of interfering with the DNA, there's a little messenger mechanism that takes the DNA, chops out pieces of the DNA to get to the cell, delivering only what the cell needs, and that's called messenger RNA. And there's a trial now for Usher's that actually masks that mutation. So instead of the gene reading it, it's like if you've got a copy of text and you've taken out the ands and the buts, you'll still understand it. So even if you've taken out a few letters here and there, the gist of it, you'll understand the meaning, and that's what actually they're doing with this microRNA editing. And then, of course, there's CRISPR-Cas9, which is a natural phenomenon that bacteria have always used to disable viruses. The actual mechanism was discovered by Elizabeth Doudna 5 years ago. It's being extensively used in cancer and genome work. And last year, it was successfully edited out a gene for heart disease, but the embryos were not implanted into a human womb because there is a moratorium on human embryo work. Because if you edit the genes in an embryo, you're actually changing the germline of that person and all their offspring. But the good news is there's a phase 1 clinical trial for Leber's congenital amaurosis, which is not Stargardts, but actually a worse disease, and they're actually editing out inpatient, and it's gone into a phase 1 clinical trial. So a lot of people ask me, how do I get onto a clinical trial? Well, let me tell you, first of all, that a clinical trial is not a treatment. Most trials are masked. In other words, some people will get the intervention and some people will get a placebo. If it's a double masked trial, even the doctors won't know who's getting what. So to get onto a clinical trial, you need a genetic diagnosis. Even if it's not a gene therapy, they need to know in a clinical trial that they're treating Stargardt's people and not RP or Usher's people, because they've got to compare like with like. And if you've got a very rare condition, you should be recruiting your family members, because the more people that we've got that are available, we can bring clinical trials to this country. Phase 1, you can't go overseas to join a phase 1 clinical trial. You've got to live close to the clinic, because if it's a phase 1 clinical trial, it's for safety. So you're checked regularly. So you actually got to live close to the clinic. If that's successful, as we said, you can move to a phase 2, and then sometimes they might need to go to multi-centers. But especially for phase 3, when they need large numbers of people, that's when we can attract a clinical trial to South Africa. So we need to build up our cohort of patients here. And of course, if you go onto a clinical trial, you need to comply with all the inclusion criteria. And we were very successful in getting a clinical trial for Stargardts to South Africa. It's Emixustat, which is a vision disruptor drug, and it's in phase 2/3. It's double masked, so some people are getting the placebo and some people are getting the drug, and even the doctors don't know who. The daily tablet for 2 years. So when we were asked to participate, we looked at our data, and we had 320 of our members who were over the age of 16 with a clinical diagnosis of Stargardts, and that was the first criteria. Then we looked at them and said, okay, now they say you have to have a genetic diagnosis, and 250 of the Stargardts people did have a genetic diagnosis. That was the second criteria. Then we wrote to those people and said, would you please go to your optometrist and get your vision acuity tested, your best corrected visual acuity. And there was a certain level, and people who had that level of vision were able to go forward to the next one, and that was the third criteria. So of those 90 people, they had to go and have a second test to check the size of the lesions. Remember, we said that the waste product builds up as lipofuscin in the pigment epithelium, and you can actually measure the size of those little lesions. And they had to have lesions that were measurable below a certain size. And that's the outcomes of this trial. Over 2 years, will those specifically, and they will know exactly where they are because they look at the same with the same machine, are those lesions growing bigger or smaller or staying the same size? And that's going to be the criteria that they will judge this. And the good news is, out of the 30 clinical sites all over the world, we had the most patients going into the trial, which was 30 patients. So you can see from 320 down to 30 how difficult it is to get people into clinical trial. But I want to tell you, please be careful. Be careful of the quacks, the scams, and the internet. Do not believe everything you see on the internet. Anybody can put anything on the internet. Remember that clinical trials are free. If anybody wants to charge you to go on a clinical trial, it's not a clinical trial. All registered clinical trials have a registration number, an FDA or an EMA European number, and if you haven't got that, it's not a clinical trial. If someone is selling you a medically approved treatment, please request results from medical journals or clinical trials. Otherwise, it's not a medically approved treatment. And if an intervention has not been tested on your specific condition, please assume that it's not safe to use. I have so many people who tell them they've got Stargardt's disease and they're taking Ocuvite. Please don't. Ocuvite is designed and tested on people with age-related macular degeneration. There are no long-term trials on the safety of Ocuvite for Stargardt patients. If you're having acupuncture or microcurrent stimulation, the researchers presume that it stimulates the growth factors, which may temporarily improve vision. So if you're having microcurrent stimulation, you've found that you've got to keep going back, and the researchers are not sure of the long-term effect of this constant overstimulation of the retina. So please be careful. If you're not sure of anything, please contact us. So why do you need a genetic diagnosis? Well, we need to identify precisely what gene it is and the management. We also need to know the type of inheritance so that we can look at family members who are at risk. And if you have got Stargardts and you want to have a family, if you know your precise genetic mutations, then you can have your spouse tested. And then you've got many reproductive choices like IVF and PGD. And then, of course, if you've got a genetic result, you can be possibly included in a therapy trial, because we know that future therapy will be gene-specific and perhaps even mutation-specific. So I want to just acknowledge the University of Cape Town, Professor Raj in the front center with his wonderful team of gene hunters has really brought us to where we are today in genetic diagnosis and genetic understanding. So please protect your vision. Ultraviolet and blue light. You know that every screen that you use emits blue light, and you should have protection on your lenses, but the rule of 20-20-20 applies. Don't look at your screen for more than 20 minutes. Look away for 20 seconds and try and look as far as you can, around 20 feet. And also look at a white wall that also rests your eyes. I also say drink lots of water, and then you have to go to the toilet often, which gets you away from your screen. Please don't smoke. The worst thing you can do for your vision is to smoke. Excuse me, I'm going to cough. Also, the researchers accept that antioxidant stress, oxidative stress, is common to all forms of retinal degeneration. And we know that antioxidants do slow the rate of degeneration. Retina Plus for IRD, and I know that not all Stargardt's patients can take Retina Plus. So if you can't take Retina Plus, make sure that you're eating lots of leafy green vegetables like kale and spinach. You must not have any supplements that contain vitamin A. If you've got Stargardt's or cone-rod dystrophy, and if you don't know if you've got ABCA4 mutation or not, presume that you have. If you take it, I've shown you how the vitamin A will increase the toxic vitamin A, and you're only going to be adding to that. Reduce your food additives, preservatives, flavoring, coloring. It's really, those are nerve poisons. Eat as naturally as you can. Have a healthy diet. Be physically fit. We know if you're physically fit, you're actually better. Your vision is better, your health is better. And sleep is very important. We don't grow new photoreceptors. We're born with our full complement. But when you sleep, in your deep sleep, between 11 and about 3 in the morning, the discs within the photoreceptors are regenerated. So what does Retina South Africa do? We identify patients, we inform, educate, counsel, and support, and intervene. And Anton is going to speak to you just now about apps and assistive devices. We have a confidential patient registry. We facilitate gene testing, and we collaborate with clinicians and researchers all over the world. Your take-home message is, have an accurate clinical diagnosis. You should have a genetic diagnosis because personalised medicine is coming even to South Africa. Please support Retina South Africa, and if you've got a genetic result, even if you haven't, you must register with myretinatracker.org. It's very important. So how can you help us? You can nominate Retina South Africa as your beneficiary at my school, no charge to you. You can also take a ticket in our Circle of Light. For a year's subscription of 250 Rand, you can win 500 Rand per month. You can support us by paying your membership fees and giving us donations, and also you can get all your friends to donate, and any donation over 250 Rand will get them a tax deduction certificate, and now's the time to do it. And we'd like to thank you very much for your attention. And now we will go on to Anton van Rooyen. Anton is the most amazing person. He knows so much about all the assistive devices. You're going to do a 2-minute introduction, aren't you, Anton?
I can do that, yes, sure thing.
Right, so Anton, over to you.
Okay, hi everybody. Nice to talk to you, and yeah, as I said, please ask me questions, because first of all, we all have different needs, that we things that's a problem to us, and we have different needs where we need help. So it doesn't help having an overall thing of all assistive devices will be here for the rest of the day. So if you've got a specific need, let's look at that and then apply what would be the best and the most economical or even free if possible. There's so much in assistive devices, but luckily for us, with the advent of the smartphones and apps, life has got a lot cheaper and easier. So I think let's go to questions in that case.
Okay, thank you, Anton. I'm going to kick off with the first question for you. We know that you use ZoomText a lot, but a lot of people are reluctant to pay for apps when there is so much stuff available free. Can you comment on or suggest a reasonable alternative that is free?
Let's just get it clear. ZoomText is a magnifier and reader, i.e. your screen gets magnified to whatever size. So you're still using the eye to find your way around. Then it's got the reader, which will speak to you. As opposed to something like JAWS, which only really speaks to you. So that's for people who can't see the screen anymore. However, JAWS is, its quality of reading is higher than ZoomText. ZoomText actually don't refer to it as a screen reader, they refer to it as speech. So it's magnification with speech. So it's really made for the partially sighted person. Unfortunately, there isn't. The only real free thing is NVDA, which is equivalent to JAWS. It is not a magnifier screen reader. However, there are things on Microsoft, on Windows, where you can magnify text to a certain extent, accessibility options in things like that, but it's not anywhere near what something like ZoomText can do. Unfortunately, ZoomText is expensive, like JAWS, etc. And I just want to make a point that I made many years ago. I got to a point where I had to decide, ZoomText is there. Am I going to keep on being able to work? If I'm going to keep on working, I've got to get ZoomText. It's like a rep saying, I can't afford to buy a car. There are times when you first have to look at why you need it and how you're going to get it, and then worry about the money side or the expense side of it, depending how important it is to you. If you just want a ZoomText to read Facebook or something, I'll say it's not necessary, but when it's going to keep you working and earning a living, sure, make a plan.
Thank you.
I've got a question from Ingrid who says, can JAWS be used on an Apple/Mac?
No. I'm not going to put my head on it, but I think, I don't know. I don't use Apple Mac, so I can't afford them, so
but
I don't know.
Perhaps if Ingrid drops a line to the office, at head office at retinasa.org.za, so we will check that out, Ingrid, for you. Thank you.
Thank you. And the next question is for Claudette. It comes from Tracy. Our son has Stargardts, but only his father has Stargardts. The mother is not a carrier. How is that possible?
That's a really good question. There are rare forms of dominant Stargardts, but we also have this anomaly with Stargardts, with the ABCA4 mutation. Normally, you have 2 copies of a mutation. So you'll get 1 mutation from your mum and 1 mutation from your father. But some people have got 3 mutations. And even though we know it's mostly a recessive condition, if you've got 3 mutations, your child might inherit 2 of those 3 mutations and still have Stargardts. So we do need to look into the family, check the parents. Is the mother definitely not a carrier? Because if the father is affected and the mother's a carrier, then the child is at very high risk of inheriting from both mother and father. So again, please email the office and we will certainly look at your family. And if you haven't had a genetic test, I would advise you to have one.
Thank you, Claudette. How long before we will have a cure? Comes from Ilsa.
Well, that's quite interesting. People who know me will tell you I'll say 5 years. But someone who knows me very well says, come on, Claudette, you've been saying that for 40 years. I showed you how long the journey is. But the good news is that every time we find something, even in another condition, it helps the journey along. I think, for example, the vision disruptor trial like we're on, Emixustat, is going to be available within definitely the next probably 4 to 5 years. But you know, research is a funny thing. We can find something like this CRISPR-Cas9 that nobody knew existed, and suddenly the whole scenario can change. The only thing I can say is the more patients who register, the more patients who have genetic testing, the more support we get from our constituency, the more likely we are to bring clinical trials to this country, and we only bring bona fide clinical trials. So we all need to help the process along.
Great. Thank you, Claudette. And then Marina has her hand up. She would like to comment or ask a question. Marina, you can go ahead. Carry on.
Sorry. My question is for Anton around the use of Zoom Fusion or Natural Dragon. So Zoom Fusion is Zoom plus JAWS brought together, and Dragon or Natural Dragon is a voice operated system, but I wasn't sure if it had screen reading built into its capabilities, because I'm considering going back to university, but I know my vision's quite severe and I would like to find the best software.
Zoom Fusion is really a combination of your Zoom text as we know it, but they've added JAWS onto it. So what you've got there is you've got the magnification side of Zoom text plus a far more powerful screen reader than what the normal Zoom text would have. It's, I think, possibly the best option on your computer to use. Dragon is, you can speak to your computer and it'll take those stuff. Now, on Windows, you can, to a certain extent, do it anyway. And as I've said, the accessibility features on something like Windows, they're there, but the magnification, for instance, or the text enlarging wouldn't be at the same level as Zoom text, and therefore speech, like NVDA or speech on your Windows wouldn't be as good as JAWS. That's why you pay so much money for it. Now, the same thing applies to Dragon. Dragon would be far better, but you're going to pay a price for it.
Thank you, Anton. Claudette, the next question is for you from Rodney. If a cure is found for Stargardts, will it be affordable for the average South African family?
Well, there's that answer nobody can tell you, because we don't know where the first treatments will come from. We know that the vision disruptor drugs, which are going to slow down that build-up of lipofuscin, are going to be very inexpensive, and it's a drug. But look at stem cells, where you're actually going to take living cells and grow new photoreceptors. That is not going to be a cheap process. Gene therapy, I will tell you that the first gene therapy for Leber's congenital amaurosis, RPE65, has been approved by the FDA and the EMA in Europe, and it costs for 2 hours 11 million rand. So everybody's going to say, oh, let's give up and go home now. But that is the first, and it took 10 years for those clinical trials. So the person and the trial changed hands 5 times. So everybody's had to pay the people who did the previous research. I don't think that gene therapy in the long term will cost that much, and particularly when we get these type of messenger RNAs. It's like putting a bandage over a scar. The scar would still be there, but the eye won't see it. And those messenger RNA, where they actually put a patch over the DNA mistake, are probably going to be much cheaper. CRISPR-Cas9, which is gene editing, is going to be much cheaper. Certain things will be affordable, but you know, it's like any disease. Some treatments will be affordable and some won't. I think that somebody else asked a question that said, my son is 15 when we started talking about clinical trials, and he's now 16, and will he be available for the next clinical trial? We don't know. A year in retinal research is nothing. It's a blink of an eye. But, for example, if this Emixustat trial that we're on, if it's really successful, the regulators might say, because it's an orphan disease, they fast track it. So an orphan disease is a disease that affects less than 1 in 10,000 in the population, and Stargardts is right there in that classification. Stargardts is an orphan disease or a rare disease, and it will be fast-tracked. The regulators are trying their utmost to make sure that they are trying to help the researchers to bring these to market. We don't even know if there's going to be a phase 3 Emixustat trial, but certainly if people comply, and you can only get into a clinical trial over the age of 16, because that is considered the age of consent, and only in rare cases like the RPE65 have they treated younger children than that. The long and the short of it is, we don't really know. But what we're saying to people is, help us get there quicker. Register with Retina South Africa. If you know other Stargardt people or your family members who are not registered, get them to register. We've just been approached by a second trial organizer to say, how many Stargardt patients have you got on your books? The more patients we've got, the more of them who've got a genetic result, the more attractive we are for people to bring clinical trials to this country. So it's up to everybody. So yeah, please help us get there.
Thank you, Claudette. The next question is back to Anton again. With regard to assistive software on mobile devices, there is seeing AI and KNFB reader. Is there anything else that is available for printed text-to-speech conversion?
Yeah, as you say, there's a KNFB reader, there's Seeing AI, Envision AI. There's quite a lot of them. KNFB reader costs money. It's therefore better developed than the others. But I wouldn't jump out and go and buy KNFB reader. It depends on your uses. Seeing AI's document reader does the job. However, Envision AI on the document reader side has got a couple of nicer little features. And of course, KNFB reader has got a lot nicer features, but it depends what you wanted to do. So actually, when you get a free app like Seeing AI, try that one first and see if it does the job for me. If it doesn't, well, the Envision costs a little bit, but not anything too hectic, whereas KNFB is expensive compared to the others. But there's a lot of other apps that you can use as document readers, depending what you need it to read. But I would start with Seeing AI, see if it works for you. If it doesn't, move up to the next one. I've got a bunch of these apps on my website, and people can go and look at the different apps available.
Thank you. That's very generous of you, Anton. Jackie says, how will I know I cannot take Retina Plus?
You could try it. If it doesn't agree with you, you'll know within a month or two. We don't know why it doesn't agree, but for example, when vitamin A came out for RP, it was all the rage, and when I took it, I broke out in the most horrible hives. So I knew vitamin A was not for me. So it's not going to kill you, but it might just not agree with you. You might feel your tummy might not be good. Try it. It's natural products. It's lutein and zeaxanthin, which are the carotenoids that you get in the green leafy vegetables. And then you've also got two very powerful naturally occurring antioxidants called alpha-lipoic acid and L-glutathione that you get in foods. So try it. And if you want to know where to get it from, just drop a mail to the office and order 2 bottles and see. It's 2 months supply. And after that, you should know. People have said, but I've been taking it for 3 years and it hasn't helped. And we say, well, how do you know? You can't take it for 1 hour because you're taking it internally. But I do know that after I started taking it, I had a slight improvement in my vision. So it's worth a try. There's also a comment from somebody who said we've been waiting for 6 years now. And as I said to the lady who commented for 1 year, 6 years is really the blink of an eye. We've been at this for 40 years, not losing hope, raising money, raising awareness, doing genetic testing. And we really need everybody to get on board and make that 5 years.
Claudette, I think you've answered the next one as well. How do we get involved with gene therapy? I think you answered by encouraging people to join Retina, etc.
And also My Retina Tracker. It's www.myretinatracker.org, and it's going to be in the next e-news. Please register with them because it's a very confidential portal. Researchers are looking for people particularly with different genetic results and different conditions, and they will see the patient. They won't be able to see you. They will email My Retina Tracker, who will email you and say, Dr. van Rooyen wants to get hold of you. Are you interested? Here's his email address. So it's always in your hand. There's a question about Supernova. And I think Supernova low vision software is also an option for Apple software. And again, I don't know that. And Anton, do you know?
It could very well be. Supernova is Dolphin software, and they cover everything. They like a Zoom text, but with the JAWS level of speech. So Dolphin's very good. It's just another one. And they very well may be compatible with Apple Macs and stuff like that. But once again, we must just confirm that.
So can I just go back to the person who asked about gene therapy? If you're a member of Retina South Africa, you should have a genetic test. And if you're interested, you can find out by emailing our office. And Anton, can you just say something about Be My Eyes? Because I think that's great.
Yeah, Be My Eyes is one of the real great apps that have come out, and it's really a community thing. It's once again, it's a free app, and how it works is there's 2 ways that you join up. You obviously download the app onto your phone and you register, but now you can register as somebody who's affected or needs help. The other side of it is you're a person who's willing to help. So now what happens? I'm in a shop, I'm looking for a specific item on the shelf. I open Be My Eyes, it calls somebody somewhere in the world, whoever signed up and they're willing to help. And it keeps track of your time zones and your language. And somebody will answer somewhere and you'll say to that person, look, I'm looking for the tins of baked beans. And the person will say, okay, just hold the photo, your camera towards the shelf and move it along. And they'll say, okay, that's the baked beans you're looking for. I've used it where I couldn't see something on my screen. I'd call up and people are just magnificent. I think there's something like 1.5 million people on there who's willing to help. It doesn't cost you anything. And they've also got another section to it where you can ask for specific help. Like if you've got problems with Windows, there's a place where you can go. Microsoft has got, I think they've got a 24-hour service where you'll then be put in contact with a person at Microsoft and they'll help you through whatever you need. Be My Eyes is such a human thing that they've done, which is really great.
There's a question here from me. We do have a genetic test. So please email head office at retinasa.org.za and ask them to send it through to me and give me your full name, your ID number and the name of the patient and I will certainly look into it, because there are some of these rare genes that are being looked at now, and we'll certainly investigate it for you. And I think we took time, so I would just like to say thank you very much to Karen and Anton for joining me, and I hope you've enjoyed this session. Thank you, everybody. Anton has put his email up. It's info@siteseekers.coza. Thank you, everybody, and we hope you've enjoyed this seminar, and we look forward to talking to you virtually again one of these days. Good night, everybody.